Hello and welcome back to the second unit review. Today's unit review video will be focusing on Unit 2, Functions as the Cornerstone of Algebra. So in this video, we will do, just like I did in the last video, we'll have a lesson overview. It's basically what did we learn in this particular unit. We'll focus on what the Common Core standards are going to be for a brief moment. Look at some basic terminology that are really crucial to this unit. And then we'll do some topical reviews before summing up the most important features of this unit. So in this unit we had 7 different lessons, and the basis of this unit was really an introduction to the very basics of functions, the notation, domain and range, one-to-one, inverse functions, and starting to look at key features of functions based upon their graphs. These are the 3 Common Core standards that are associated with this unit, and as I mentioned before, these standards are going to be used throughout the entire year, so you're going to see these again and again. But for this particular unit, there's a big focus on being able to find the inverse of functions, and whether or not there is an inverse function. Another big focus in this unit was looking at the relationship between 2 quantities based upon 2 graphs or tables or equations, and basically being able to sketch the graphs and show the key features such as intercepts, intervals where it's increasing, decreasing, positive or negative, relative max and min, symmetries, and behaviors and periodicity. And then the last thing is given 2 functions represented in different ways, so maybe one's an equation, one is in a table form, or maybe one is graphed and one is in an equation form, being able to examine and compare key aspects of those graphs. Okay, so let's look at some basic terminology. Function, that is a very important term for you to be able to understand in order to do anything really with this unit, because you need to know what a function is and how to determine if something is a function or not. The basic idea of a function is that each input has only one output. So we saw equations, we saw graphs, we saw tables. If I draw in a domain A and a range B, a function occurs whenever each input goes to only one output. Okay, you can have the same output from different inputs, but each input can only have one output. So something that is not a function would look like something like this. Again, domain A and domain range B. Say you have 2 elements in A, but let's say that a third mapping comes from the same element in the domain. That is not a function, because this right here maps to 2 different output values. Some other terminology, domain and range. Okay, domain are just all the possible input values you can have into your function. And the range are all the possible output values. Okay, so let's look at some notations for domain and range. Very frequently for a lot of functions, especially polynomials, quadratics, and so forth, the domain and range of some of these functions are all real numbers, meaning you can put anything you want into the function or you can get anything out. And we notate that with this capital R, stands for all real numbers. Sometimes you'll see things like such as x is the element of all real numbers. Okay, but this is all real numbers. When there are restrictions on the domain, saying only certain x values will work or only certain y values will be in the outputs, we can use other types of notations to indicate that. Set builder, inequalities, interval notation. Okay. Set builder notation is where you have the set notation. Okay, that's just the squiggly brackets. For the domain, you say something like x such that vertical line means such that, and then you put the conditions. So you could have something like x is greater than or equal to 10. Or you can have something like x such that x can't be 5. That implies it can be anything else other than 5, but just can't be 5. Okay, and this also can work for range as well. You could say, for instance, all the y values such that y is less than or equal to 0. Inequality notation, that's just simply the same thing as sepilin notation, just without the set brackets. So you just say something like x is greater than or equal to 10, or x is not equal to 5, or y is less than or equal to 0. Interval notation looks a little strange, but that's where you use the brackets and the parentheses. The parentheses means you don't include the values. And the brackets means you include the values. So if I see something like this, this is equivalent to greater than or equal to 10, because the brackets at the 10 means you can include it, and then the infinity means that's as far as you're going. Okay, you go on forever past 10. Now note that whenever you have infinity, you'll always have a parenthesis, because infinity is not a numerical value, it is a concept. Okay, so you'll never have a bracket at infinity. And another thing with interval notation that's crucial is that you would have the small number come first, and then the next largest number come next. Okay. Now this represents, as I said, x is greater than or equal to 10. That's the inequality equivalent. So if I want to just have x is greater than 10, then I write with the parentheses. If I want to have the inequality -3 less than or equal to x less than 7, then I would put a bracket first because the -3 is included with the less than or equal to, and then I would put the parenthesis with the 7. Okay. And if I had like negative infinity to 0, I might have something like this. This represents y is less than or equal to 0. Okay, now let's look at identifying functions. Now for identifying functions, that's a crucial thing to be able to do. Determine whether or not a relationship is a function or not. And it's easier to determine if it's not a function and to be able to prove it's not a function before proving that it is a function. Because in order to prove that it's not a function, you just have to find one case where the function definition does not hold, meaning that each input has only one output. Graphically, you do something called the vertical line test. Okay. If you have a function and you draw a vertical line and it passes through more than one location, then that is not a function. And the vertical test is really helpful because what you're really looking for is you're looking for just one case, one location, one line that provides two different outputs for the same input. And the vertical line represents one particular input, and where it crosses are all the possible outputs. So if I have a graph such as this right here, notice there's absolutely no place that I can find to draw a line that will give me two outputs that will have a vertical line cross twice. So this is a function. Okay, now let's look at determining from the table values. So each input are the x values. So again, you're looking for any place where you have the same x value given two output values. It's easier to look for something that's not a function than it is a function. So if I have -1, 0, -1, 2, 5, 4, 3, 1, okay. Notice here that we have two x values, the negative ones that provide two different outputs. This is an example of not a function. So what you're looking for are repeated x's with different y's. Now, on the contrary, if I had a table that said this, -1, 0, -1, and 2, but the y values were 5, 4, 5, 1, notice that table's indicating that the -1 input still has the same output. So this would be a function. Okay. So for tables, you're looking to see if the same input gives different outputs to provide enough evidence that it is not a function. And all you're looking for is just one case where that happens. For equations, okay, again, it's easy to determine ones that are not functions first. Okay, and the general rules for the ones that aren't functions are anything where the y has an even exponent, such as the equation y squared is equal to x plus 3. Okay. That is not a function. Okay. And then another one where it is not a function is when y has an absolute value. For instance, absolute value of y is equal to x plus 3. This is also not a function. Okay. Now, what you're really testing is to see if there's a chance you can plug in multiple values of y to get the same input. Okay? Because if the same input goes to two different y's, then you know you don't have a function. And for instance, in this case, I can plug in a positive or negative result for y, and when I square it, I get the exact same number. Same thing when I take the absolute value of y. If I have a negative and a positive value, it becomes the same number in the long run. So those are not going to be functions. Now, another big thing about this unit was function notation. Proper function notation uses stuff like f of x, g of x, a of x. Doesn't matter if they're lowercase or uppercase, v of x. The most common ones are f of x and g of x and h of x. But if you're talking about the area of a function, in terms of functions, then you might say a of x for area or v of x for a volume of a figure. But you know, the important things in here is that this f, whatever letter you use to determine it, is just the name of the function. And that allows you to have several different functions in terms of the same variable. Okay, and then inside the parentheses is your variable that is your input. Okay. So proper function notation has that starting off. So you might see something like f of x is equal to square root of x minus 5. Or you might see a of x is equal to x squared plus 3x, make it a little better, x squared plus 3x minus 7. You might also have things like piecewise functions, like f of x is divided up into two different parts. Maybe one is x minus 7, the other part is 3x plus 2. Those are two linear functions. But to make sure it's a function and each input only has one output, you have to state the domains for each part of the piecewise function. So for instance, this first one might be for all x values less than 5, and the rest of it's x greater than or equal to 5. Okay, notice there is no overlap. There are no two x values. Just as a side note, what would not make this a function is if I put an equal sign with that first one, because that means I can plug 5 into either one of those, and I might get two different outputs. In the top one I get -2, and the bottom one I get 17. And you can't have two outputs. Okay. But more on piecewise functions later. Okay. Evaluating a function, all you have to do is just plug it in to the function. So let's say I have, let me provide a different example. Let's say I have f of x is x cubed minus 5. If I want to evaluate the function for the input of negative 3, I plug in negative 3 for all the x values. So f of 3 is evaluating the function at negative 3. Now when you do this, make sure you put parentheses around your input values. Okay, and this will help avoid any kind of calculator mistakes, especially when you're dealing with squaring and raising to the 4th power, any kind of even power or absolute values. Okay, you want to make sure you put the parentheses in the right spot. So that would give us 27 minus 5, which is 22. Now likewise, if I had g of negative 2 into x squared plus 5x plus 3, that would mean that I would have negative 2 in parentheses squared plus 5 times negative 2 plus 3. 4 minus 10 plus 3. Negative 6 plus 3 is negative 3. Now in your answers, when you're asked to evaluate them, you should always write your answer like this. G of negative 2 is equal to negative 3. Use that notation. So you say f of negative 3 is equal to 22. That's how you can write your answers for these. Okay. Function composition. Now, proper function notation, there are two ways you can notate them. One is using what's called fog notation, and the other one is the typical function notation. So here is how it's typically done. F of g of x. What you're doing is you're evaluating a function at another function. Okay. And what you have to do first is you have to first evaluate g, then f of x. You have to go inwards, outwards, or right to left. Okay. The other way you can notate this is f of g. That's the fog notation because it looks like a little O, but it's really the composition symbol of x. Same thing. Evaluate g, then f of x. You could evaluate compositions of functions in terms of x, keeping the variable there, or you could evaluate them in terms of numbers. So let's just say I have two functions. F of x is 2x plus 6, and let's say I have g of x is 3x minus 5. If I were to say find f of g of x, notice I'm not evaluating any kind of numbers, I'm just evaluating f of g of x. So what I'm going to do is I'm going to plug in 3x minus 5 into f, because 3x minus 5 is the g of x. So then it looks like something like this. And again, remember when you're evaluating, keep the parentheses there, because in this case especially, you're going to be dealing with distributing terms. So you have 3x minus 5, 2 times 3x minus 5 plus 6. And therefore, if you continue to do some work, you get 6x minus 10 plus 6. So you get a final answer. F of g of x is equal to 6x minus 4. Now just to show you that it does not always necessarily work the same if you flip them, I'm going to evaluate g of f of x. So what I'm going to do now is I'm going to evaluate g at 2x plus 6. So g is 3x minus 5, so I'm going to do 3 times 2x plus 6 minus 5. 6x plus 18 minus 5. So that gives me g of f of x is 6x plus 13. Notice they were different, right? F of g of x is not the same as g of f of x. Order is important when you're evaluating these. Okay, now looking at evaluating at values, say I say, let's do f of g of 3. You still have to do the same thing. You have to evaluate g first at 3. Okay, so I'm going to do that on the side. G of 3 is 3 times 3 minus 5, 9 minus 5, which is 4. So this g of 3 is equivalent to 4, so I'm going to really evaluating f at 4. So that I do 2 times 4 plus 6, 8 plus 6, which is 14. So then I say f of g of 3 is equal to 14. Oh no, that's underneath all that desktop trial stuff. Okay, hopefully you can see that. I'll rewrite it up here. I wrote this down. F of g of x is equal to 14. That came from there. Now you could also do this with fog notation. You don't have to just do it with the general composition notation. Let's talk about another important concept, one-to-one functions. Okay. One-to-one functions is, the definition is formally that different inputs imply different outputs. Okay. So if you had, let's say 3, which is not equal to 5, okay, those are two different inputs, it's implied that f of 3 will not be equal to f of 5. Okay. Meaning that each output is only used once. Okay, there's only a one-to-one mapping, meaning if you go one way to the other, you have a function. Okay. So, and the way we test to see if something is a one-to-one is we use something called the horizontal line test. Because the horizontal line test, if you were to find two values that intersected the graph from the horizontal line, then that means that different outputs gave the same, different inputs. This is x1, this is x2. They gave the exact same output, so that fails a horizontal line test, and that also says that it is not one-to-one. Again, just like with functions, determining if they're functions or not, it's easier to determine if something's not one-to-one than it is one-to-one. Okay. So if I have a graph like this, all I have to do is locate one place that fails the horizontal line test. Okay, and in doing so, here's a place. This actually goes through several places. There, there, and maybe even there. Okay. So maybe up to 3 times. So that is not 1-to-1. Now an example that is 1-to-1 might be something like this. Okay. You have that function. There's absolutely no place where you can draw a horizontal line that goes through more than once. And notice there's no place we can draw a vertical line going through more than once. So this is a function, and it's also a one-to-one function. Just take a note, things like this, sideways parabolas, they will pass the horizontal line test. But this is still not one-to-one function because it is not a function. It fails the vertical line test. Okay, so just be careful. Just because it passes the horizontal line test does not mean it's one-to-one. So make a little note saying that it must pass both the vertical line test and the horizontal line test to be 1-to-1. Now let's look at inverse functions. Okay, inverse functions. It's very important to note that every function has an inverse. Okay, every function has an inverse. However, the question depends whether or not the inverse is a function itself. Okay, so in order to determine the existence of an inverse function, you must first have something that's 1 to 1. And that, if you think about it, it makes a little sense, because in order to find an inverse function, you switch the x and y variables and then solve for y. So the inverse is found by switching x and y. So that means in order for it to be a function, it needs to pass the horizontal and vertical line test to begin with. Okay, vertical line test means that the original one's a function. Horizontal line test means it's 1 to 1. Okay. Because the horizontal line test becomes the vertical line test in the inverse function. Okay. So it must be 1 to 1 in order to have an inverse that is a function. Now, to find an inverse function in terms of x and y, say I have the line y equals 1/2 x plus 3. And I'm asked to find its inverse. What I'm going to do is I'm going to switch the x and the y, so I'm going to write it as x equals 1/2 y plus 3, and just solve it for y. Okay, so I would subtract the 3, and then I would multiply everything by 2. Remember to indicate multiplying both sides by 2 to give you 2x minus 6 is equal to y. Okay. And that would be my inverse function. Now, to use proper inverse function notation, okay, so you can represent equations with y and x's, but if you're asked to use function notation, then you would be given something like f of x is equal to 1/2 x plus 3. And the function notation is going to be f to the negative 1 of x. Make that look a little better. F to the negative 1 of x. That represents the inverse of f. In this case, we found it to be 2x minus 6. Now, don't confuse that negative 1 as making it reciprocal with a positive exponent, because when we saw things like x to the negative 3rd, we made that as 1 over x to the 3rd. That is a different type of concept. This negative 1 is just a notation. Now, because the x and y values switch, what that means with the inverse functions is that the domain of a function, which are the x values, becomes the range of the inverse. Likewise, the range of a function becomes the domain of the inverse. Ooh, and I just noticed I spelled inverse wrong. Oops, above. Okay, so for instance, if f of x had a domain and a range, let's say negative 5 is less than or equal to x less than 7, and the range was 5 less than y less than or equal to 15. For the inverse of that function, the domain becomes 5 is less than x is less than or equal to 15. Notice that it becomes from the range, it comes from the range, goes to the domain. And the domain of the original function becomes the range of the inverse. Negative 5 is less than or equal to y is less than 7. Okay, but notice, of course, domains are always x values, ranges are always y values. So when you switch the domain and range, you have to make sure you put the appropriate variable there. Okay. And there's other ways you can identify or find inverse functions or verify that they're inverse functions. The graphs of inverse functions, because you switch in the x and y, are really always going to be a reflection through the y equals x line. Okay, if you can reflect any kind of graph through that line, you're going to find its inverse. So the way you can find an inverse through points is if you're given like the 0.53, that means that it goes to 3, 5 on its inverse. If you have negative 7 comma 5, that goes to 5, negative 7. Okay. There's another way you can verify if something is an inverse by using composition. Say you are given f of x and g of x. And the question is g of x the inverse of the function f? Okay. What you're going to do then is you're going to evaluate the composition of functions. Now if they are inverses, then that means that you should get x. If you get that, then f and g are inverses. Okay, so I forgot to put that in the slide, but it's an important thing to point out. That evaluating the compositions of two functions, if you get x, that verifies that you have inverse functions, because you're plugging in a y value when you're evaluating one function, essentially, and if you get an x out, that means the x's and y's switched. You get the x back. Okay, and the last thing I want to focus on are the key features of functions and their graphs. Okay, and being able to look at the graphs, a lot of these are pretty obvious. Okay, but let's just say I have a graph that looks like this. That's a nice polynomial graph. Let's say it goes through at negative 10, negative 3, negative 2 on the y-axis, and then 5 on the x. The x-intercepts are just wherever the output is 0. Wherever the y value is 0. Y's are the outputs. So if you're given an equation, let's just say I have f of x. This doesn't match up with the graph I drew, but let's say I have f of x is equal to 3x minus 6. Okay. The y is equal to 0 wherever f of x is equal to 0. To solve for the x-intercepts, I would do 0 is equal to 3x minus 6. And then solve for x. So I get 3x equals positive 6, adding 6 to both sides, x equals 2. So in this case, the x-intercept is 2. Y-intercepts are found wherever the x is equal to 0. So what I'm going to do is I'm going to substitute 0 in for x. I'm evaluating f of 0 essentially. So using the same example above, 3 times 0 minus 6, 0 minus 6, negative 6. So the y-intercept is negative 6. Now zeros or roots are really the same thing as the x-intercept, so it's wherever it crosses the x-axis. Okay, so 0 in this case is 2. For the graph that I drew, let's say this is function g of x. The x-intercepts in this case are going to be where the y is equal to 0, and now it's on the x-axis. Negative 10, negative 3, and positive 5. And the y-intercepts are going to be just negative 2. Now note, for functions, there can be multiple x-intercepts, but there can be only one y-intercept. It's a nice little thing to notice. Because if you had more than one, then it would fail the vertical line test and you wouldn't have a function. Okay, so there's only one y-intercept for every function. Now let's use the same example that we did previously. Let's see if I remember what I had. I had negative 10, I believe I had negative 3, negative 2, and 5. Okay, that's g of x. Now some other functions that you should be able to identify from graphs, you can use your calculator to find them, but maximum and minimums. Okay. Maximums are anywhere where it changes from increasing to decreasing. Minimums occur where it changes from decreasing to increasing. Now when you're looking at graphs, blanket spell. Alright, increasing. If you're looking at graphs, you're always going from left to right. Okay, so if you're looking where it's increasing to decreasing or decreasing to increasing, you're always looking from left to right. So maximums occur where it's increasing and then it starts to decrease. That point right there, best as I can draw it, is the maximum. From decreasing to increasing, that point right there is the minimum. The most common term you're going to refer to these are relative maximums and relative minimums. Okay. If you had an absolute maximum, there's only one of those, and that's the highest possible point on the function. So if you see a function like this, there's two maximums, but this one over here is the absolute max. Now if you're asked to find the maximum or the minimum, typically they're going to be coordinate points. If you're asked to find the maximum value or the minimum value, those are just going to be the y values of those coordinate points. Now for increasing, decreasing, okay, that's just going to be found by looking at intervals where the graph is going up as you go from left to right. Okay. So let's just say on this graph over here, I'll use this example for my things. Let's say the maximum here is going to be at maybe -6, 1, and the minimum here is maybe at 1, -4. Okay. The maximums for this graph, the max, is going to be the point -6, 1. The minimum is going to be the point 1, -4. Now the max value, well in this case there is none because it goes to infinity, and the minimum value, same thing, there is none because it goes to -infinity on the left side. Okay. Now increasing and decreasing, it's increasing wherever the graph is getting larger. So in this case, -6, 1 is a maximum. So you can think about increases from maybe a minimum to a maximum. Okay, so x less than -6 is where this graph is increasing. But notice there's also another interval where it's increasing. If you look at the point 1, -4, it's increasing after there as well. So, or x is greater than 1. Those are the intervals for which it is increasing. Now you can use any kind of notation. You could use interval notation, set builder notation, but as long as you indicate all the places where they are increasing. Okay, that's what I was looking for. Decreasing, we're going from a max value to a min value. So -6, 1 is a maximum, 1, -4 is a minimum, so it's decreasing from -6 less than x less than 1. Okay. Just one interval where it's decreasing. Now take a note that I did not include the -6 or the 1 because at those points, at the maximum and at the minimum points, it is neither increasing nor decreasing. Alright, and key features of their functions. So let's look at part 3, greater than 0, less than 0, and where the function is equal to 0. What this is greater than 0 is essentially meaning where is the function positive? Less than 0, it's where the function is negative. And equal to 0, well those are just the x-intercepts or the roots, okay, or the zeros. Where is the output 0? It's going to be at the zeros, or intercepts, x-intercepts, or roots. So if I use the exact same function that I used before, where it goes for -10, notice we're only caring about the x-intercepts, okay? Where is the function greater than 0? Well, you're looking to see where it is. If it's positive, it's above the x-axis. And this particular function is two places where it's above the x-axis. It's above from -10 to -3, and also from -5 all the way up to positive infinity. So, the intervals where it is greater than 0 are going to be -10 less than x less than -3, or x is greater than 5. And again, you can use any kind of interval notation for this. I'm just choosing to use inequality. Notice greater than 0 means I'm going to have no equal signs here. If I said greater than or equal to 0, then I would include the equal signs. Now negative is going to occur wherever the function is below the x-axis. Okay, so below the x-axis occurs here and here. So below the x-axis is x is less than -10, or -3 is less than x is less than 5. That's where the function is less than 0, or negative. Alright, now where is it equal to 0? That's just the root. So it's just going to be x equals -10, -3, and 5. Okay, so let's just look at the summary of the most important things in this lesson. Okay, so these are the things you should be able to do from this unit. You should be able to determine whether or not a relationship is a function or not. Okay. That's going to be using the vertical line test, or looking at the tables, or looking at the equations. Okay, it's easier to figure out if something's not a function. You should be able to determine if a function is one-to-one, which is the horizontal line test, or, and the vertical line test, because you have to say it's a function and one-to-one. You should be able to use proper function notation to both look at the equations of functions and the inverses, or the composition of functions. You should be able to evaluate functions and compositions of functions. You should be able to write the equation of an inverse function and find it by switching the x's and y's and solving for y's. And you should be able to state the domain and range of a function or its inverse. Remember, the inverse of a function has a switching of the domain and range. You should be able to find key values from the graph: x-intercepts, y-intercepts, zeros, roots, maximums, minimums. Okay, and you also should be able to find out where a function is positive, negative, 0, and increasing, decreasing, those kinds of things. So thank you for watching this video, and see you next time.